Hello there, this is Dr. Dell, and this is our next lesson on triangles. This is G6, lesson number 6 in geometry. And today we're going to talk about what are called similar triangles. So we're going to be dealing with two triangles at the same time, and I will tell you that this is perhaps the most important chapter in geometry, because this is something that enables us to solve all kinds of practical problems. This comes up all the time. In fact, I don't think this is given enough emphasis in a traditional geometry course, but we're certainly going to learn it here. Now, two triangles are similar if they have equal angles. That means that they are essentially the very same shape, but they're different sizes. And now, if they happen to have the same size, in addition to being similar, then they're going to be called congruent. But we're not going to worry too much about that. Similarity is what we are interested in, and here's an example. Here's a triangle, has angles 1, 2, and 3, and here's another triangle, has angles 4, 5, and 6. Now, I've tried to draw them in the notes so that they are, in fact, the same shape, and I'm going to give you that angle 1 equals angle 4, and I'm going to give you that angle 2 equals angle 5. And then that means angle 3 equals angle 6. In fact, if you have two triangles, and if you know two of the angles of one equals two of the angles of the other, they're similar, because obviously the third angles then have to be equal. Because of why? Well, they all sum to 180 degrees. So that's what similar triangles are. Now, here's the important thing that you want to learn. Suppose you have the lengths of the sides of these triangles. This is A, this is B, and this is C. And over here, this is X, and this is Y, and this is Z. I just had to give them labels. These are lengths. They could be inches or feet, but they have to be the same units of length. Then here's an interesting thing, and I make the point up here. Corresponding ratios of the lengths of the sides are always equal, and that's what makes these similar triangles so important. It's often the way you can set up an equation to find an unknown that you're going to learn when we do some problems. And then I commented that if two sets of angles are equal, the third has to be also, so they're similar. Now, let's first of all be sure you understand what corresponding sides are. That's very important, or you can make a mistake very easily. I told you that 1 and 4 were equal, so the side opposite 1 is B, and the side opposite 4 is Y, so B and Y are corresponding sides. Now, angle 2 is equal to angle 5. So what would be the corresponding sides for these two angles? Well, opposite 2 is A, opposite 5 is X, so A and X are corresponding. And of course, what's that leave? C and Z are corresponding. Well, why? Because 3 and 6 are equal. Okay. Now, it's very important that you identify what the corresponding sides are before you start doing anything with ratios. Because if you don't use corresponding sides, these are not true equations. Now, a ratio is when you divide one number by another, or one length by a number. So for example, we could take the side A, and we could take its corresponding side X, and we could take A divided by X. That's a ratio, A divided by X. Then we could take B and its corresponding side Y, and we could take its ratio, B divided by Y. And guess what? They're equal. A divided by X is equal to B divided by Y. And also, those are equal to C divided by Z, because C and Z are corresponding. So we have really, in essence here, several equations. A over X is equal to B over Y, and that's also equal to C over Z. Now we could have done something a little bit different. We could flip all these upside down. Instead of A over X, we could say X over A. But if we do that, then we have to say Y over B. Remember, you always have to be corresponding sides. So if you got X over A, you're going to have Y over B. And you got to have Z over C. This is really the same set of ratios, only flipped upside down from the first set. Now, that's not all. And which of these you use, by the way, depends on what you know and what's convenient. You could take A and B on this first triangle. A divided by B is a ratio. Now suppose, what are the corresponding sides? Well, A corresponds to X, B corresponds to Y. So you could take X over Y. And sure enough, A over B is equal to X over Y. And altogether, there's 6 such ratios. You could flip these upside down and take it b over a as y over x. B over a is y over x. You could also take c divided by a, and then what would that equal? Well, what are the corresponding sides? Z and x. So that would be z over x. Or you could have said a over c. That would have been x over z. You see what we're doing here? And finally, just to be complete, c divided by b would be what? Well, c corresponds to z, b to y, so z over b is z over y. Or b over c is y over z. So there's 6 different ratios here. In fact, the bottom 3 are the same as the top 3, only flipped upside down. Now, you can use any of those when you're solving problems with similar triangles. And what happens so often in practical math is you end up with 2 similar triangles. They're not right triangles. They're not the same size, but they do have the same angles. And maybe you know 3 of the sides that in such a way that you can then figure the corresponding sides of the others. So we're going to look at some problems that do that very thing. And you're going to be given some of these problems. This is what I want to point out. Suppose you have 2 equal ratios, and one of the things is unknown, but you know the other 3. So for example, suppose you had the unknown x divided by a was equal to b divided by c. So a, b, and c are knowns, but x is the unknown. Well, we learned in algebra this is a very simple linear equation to solve. The solution, x is just a times b over c. And then I gave you an example over here. X over 3 equals 7 over 12. That means that x equals 3 times 7 over 12, which is 1.75. And that dropped down to here. Now, a similar thing, you could put x in the denominator if you wanted to. You don't usually do that, but you could. So you have a over x is equal to b over c. Now, this is a very different equation because I put x in the denominator. Now, in this case, you have to flip them first. So you get x over a equals c over b. And then when you multiply through by a, you get x is equal to a times c over b. Notice that's different than this up here because it's a different equation. By the way, this is why formulas can be so confusing. You might remember the wrong formula. If you thought this was the solution to this equation, you would be dead wrong, and you'd get the wrong answer. In fact, as I taught you in algebra, don't rely on formulas, rely on process. So let's take an example here, and let's do the process. You know that 3 over x is equal to 7 over 12. That's a different problem than the top one, and you're going to get a different answer. Well, the first thing you do is you flip it. Get x over 3 is 12 over 7. Then multiply through by 3. We learned this in algebra, so that's why I'm going over quickly. And if you don't know this, you need to go back and review this section in algebra. So x is equal to 3. This little x here means times 12 over 7, and that turns out to be 5.15. So what you do in the real world is you try to find 2 similar triangles where the unknown is one of the sides, and then you know 3 or more sides, one of which is going to be the corresponding side to the one that you know. In other words, opposite the corresponding angle of the unknown side. So here's a couple of examples. Here is a triangle, angles 1, 2, 3, and they're equal to angles 4, 5, 6. I'm giving you that. And I know 12.3 is this side, I know 5.4, I know 3.7, and then I want to know x. Well, now you got to set up an equation. There's different ways you can do it. I showed you a couple of ways. There's actually lots of ways to do it, but it doesn't matter. Just do one of them. Just make sure you stick to corresponding sides. Take x divided by 12.3. That's for this triangle. That's a ratio. What's that going to be equal? Well, what's corresponding to x? 3.7. What's corresponding to 12.3? 5.4. So then x over 3.7 will be 12.3 over 5.4. Actually, that isn't what I did here. X divided by 12.3 then will be 3.7 divided by 5.4. And then you solve that, you get x is 12.3 times 3.7 divided by 5.4, and that turns out to be 8.4. Now, you could have done it a different way. You could have taken x over 3.7, and that would equal 12.3 over 5.4. It looks a little different, but you get the same answer. Here is a wrong mistake people sometimes make if you're careless. You mix up your sides. If you took x and divided it by 3.7, and then you took 5.4 divided by 12.3, you would have done that wrong because those aren't corresponding. If x corresponds to 3.7, then you don't want to, then 12.3 corresponds to 5.4, not vice versa. And I put this upside down, and that's an incorrect thing. Here is another example that might come up. There are many, 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 many situations where similar triangles arise. And it's wonderful when that happens because they're so easy to solve. And just here's a quick example. You got a flagpole or some kind of a pole here. And there's a sun shining, it casts a shadow, 37.3. Let's say it's feet. And then you've got another pole here. Maybe it's a human being standing here. 5.87 is the height. And it casts a shadow 3.42. The question is, how tall is the pole? Two similar triangles, because this is a shadow, so these angles will be the same. Pretty simple. X over 5.87 is equal to 37.3 over 3.42. Those are corresponding, right? This to this, this to this. Do the algebra, and you get 64 feet. So this is 64 feet tall. So this is an easy way then to measure the height of a tree or a pole or a building. Look at the shadow, measure it. Take a known height, just take a pole. Or you could just take a human being and that you know the height of, and then just look at its shadow, measure, and you know this, you know this. You can measure these two. You can measure this, then you can calculate that. And this happens all the time, and that's how similar triangles are used. And so it's easy to do. In fact, that's the beautiful thing about mathematics. Once you understand something, it's really very easy. And then if you know the right thing and apply it to the problem, you're in business. For example, how tall is the pole? Well, if you knew to do these things, to measure these two and measure this and apply similar triangles, it's a very easy problem. If you didn't know that, it might be very difficult. And I'll point out once again, suppose you didn't have this other triangle and you knew angle 1. Could you figure x? Well, if it was 30 degrees or 60 degrees, you could, but if it was anything other than 30 or 60, you couldn't if you didn't have that. And so then you would have to use something called trig, which we're going to learn in the last part of this fundamentals course. We have a whole section on trigonometry. Once again, I point out to you that trig sometimes is useful. But if you didn't know trig, then you'd have to set up a triangle over here like this and like we just did. Okay? So this is Dr. Dell signing off. You're going to have a lot of problems to do. And as always, the first one may take you a little longer, and then the next one will be faster, and then faster. And after you do 8 or 10 of these problems, you'll get very fast at them. It'll be very easy, and hopefully you will find that enjoyable. So Dr. Dell signing off. I will see you on the next lesson where we're going to talk about something other than triangles.